Now come to the limit.
Yeah.
H to 0.
Okay, the reason why it's h to 0 is look at what your h value is. It's the distance between the x coordinates of A and B, right?
Yeah.
But remember, we're trying to find a single point. I don't want 2 points. So, I want these guys to be getting closer, don't I?
Yeah, towards 0.
Yeah, how can I represent them getting closer using the letter H? How could I do that? So what Ben is asking is, why does H have to approach 0? The reason is because I want these 2 points to get closer and closer
So H
together.
is smaller.
Yeah, because their distance away from each other gets smaller, so H is approaching 0. Okay, it's getting smaller. Okay. So that was called first principles, and that's what Newton and Leibniz first discovered. When I drew the gradient function of a parabola, what did I get? Can you remind me?
Constant.
Yeah, I got a line, right? I got a line, a linear function that represents a constant change. So when I differentiate now, when I apply this process, I expect to get the equation of a line, right? Because that's what I got over here. So let's take our parabola and let's see what we get when I use this definition. The first thing though is that there's a lot of different components going on. I already have f of x. What else would I need? I need
H.
yeah, so h we can just leave as, but I need f of x plus h, right? So this is coming back to our function definition. How can I write f of x plus h using this guy? What do I have to do?
You have to double. Well, you would have to use 2, wouldn't you?
Plus H, or 2H or H squared.
Okay, so remember, anytime I use this function definition, I replace anytime I see x with what's inside here. So in this case, I have x plus h. So I replace anytime I see x with x plus h, and exactly right, Nathan. I've got x plus h all squared. It's really important that you do this whole process properly, right? So I'm replacing anytime I see x with what I see in these brackets, and that's all I've done
And it's
here.
always an H, sir.
Yep. Now let's just expand this out because it's going to make our lives a bit easier. Yep. So that's x plus h, x squared plus
I made it a bit harder.
2hx plus h squared. I'm just trying to think if this is the best way to do it. Hopefully this will work out. Okay. So I've got my 2 components. Now I want to use this derivative definition. So I'm saying the change in y over the change in x. So dy dx is equal to, I need all the components, the limit as h approaches to 0 of, I'll write the whole thing out for you so you can see what's going on. F of x plus h minus f of x all over h. Now remember, when I have this right here, I need to do some other things to it, because if I just try and substitute h as 0, I'm going to get 0 in the denominator, and that's bad. It's not really going to work out. Okay, so let's work out what I have here. I've got x squared plus 2hx plus h squared minus f of x, which is x squared, all over h. Okay? Okay, so let me just break down what I did. So I wrote down the formula first that I was using, that we developed together. And then all I did was I replaced the components that I found. I've got f of x plus h, which is this guy
The
here.
X squares cancel out.
And I've got f of x, which is this guy here. And I've just written, okay, this is my f of x plus h, and this is my f of x, okay? And I've left h as itself because I can't do anything with that. Now this actually
The X's
is going to
cancel
be,
out.
yeah, it's going to be really neat, right? Because these 2x
2x plus
squareds,
h squared.
that's just x squared minus x squared, so I can say
And
that
then the
these
H's cancel out.
cancel out.
And then you can cancel an H
Now,
out.
now, let's be really careful with cancelling, okay? What I really want you to realize is what you're doing is you're factorizing a factor of h, okay? So you're saying, all right, there's a lot of h's in common, so I've got h outside of 2x plus h. I'm just going to factorize that out, okay? Can you see that?
Yeah.
I'm just taking a factor of h out here, because all I'm left with is...
And then you can get rid of the 2 H's.
Sorry, I might have skipped a step. Is this clear how I got from here to here?
Yeah.
Yeah, okay.
And
And then you can divide through these guys.
And then you can substitute.
Yeah, then you get left with...
2x plus 0.
Right. 2x plus h, and when I find the limit now I don't have any problems with substituting h as 0, because this is just going to go away, and that's just going to leave me with
2x.
2x. And what is that an equation of?
a line, like a
Right,
line.
yeah. You found that dy dx, the gradient function, is a line with a positive gradient, which is what we have over here.
So you're gonna ever work with like real numbers?
We will in a second, because right now all we've done is just found the gradient function. But when we use numbers is when we want to find the gradient function at specific points. Okay? But let's keep going with this. Let's keep going with this idea.